before that. It was the city about 20 years I was
Always on and okay, all good.
Okay, guys, I need 5 very short answers from you. So we need to name these systems, 1, 2, 3, 4, 5. So what do we call systems that have the damping ratio greater than 1, equal to 1, less than 1, equal to 0, less than 0? So the first one, overdamped. If equal to 0, no, if equal to 1, sorry. Critically damped. Okay, this is good. Less than 1, greater than 0. equal to 0, undamped. This is good. You know, there is hope, I think. You know, you're so quick and so correct. Less than 0. Negative. Well, the damping is negative, but what do we call these systems that have a negative damping ratio? Well, there is nothing in your lecture notes, unfortunately. So I thought you would search a bit beyond what will be in the exam, but you didn't. Okay. Because this is not going to be in the exam. Well, in a way, well, we will touch on this in lecture 9. These systems are called unstable. They are unstable. So if damping ratio is negative, the systems are unstable. More about that in lecture 9. Speaking of which, I visited all tutorials today, those who were there. You could have seen me if you wanted to. And in some of those classes, I was asked about what will be in the mid-semester test. Not in all classes, obviously. Most of you don't care what will be in the mid-semester test. You will be ready anyway. But just briefly, I will make that decision after the Friday's lecture when I know how far we go. What is certain so far that tutorial sets 1 to 5 are well covered or will be definitely covered today. Maybe I should actually show those problems. Over here, tutorial sets 1 to 7. So, well, actually, tutorial set 1, since most of you got at least 2 marks, and I believe those 2 marks are for linearization, so most of you know how to linearize well, different systems. We can safely say that linearization will not be in the mid-semester test. Okay, so that's why, I mean, having the inside information, I can tell you that. But just don't spread that around. Okay, so no linearization in the mid-semester test. So we are talking now about Laplace transform, definitely. You need it one way or another. You need these problems. Set 3 modeling, definitely. There will be at least one system to model, to write a differential equation, derive transfer function, do something with that transfer function. Okay. Okay. So back to our tutorial problems, in case you don't remember what was where. In the tutorial set 1, linearization will not be in the mid-semester test. I'll put that as an announcement for those who are not here and who don't listen to the recordings of the lectures, but complain that the recordings are not available. Set 2, definitely. So all these problems may not be asked as separate questions. Find the final steady state value if the transfer function is such and such, and you put such and such. You will be truly part of a bigger question, but you can't ignore these problems. So you should know all these things because, as I said, they will appear not only in the mid-semester test, but in the final exam as well. And lectures we are going to have in the future. You are definitely going to have one modeling problem in the mid-semester test. So set 3 is also relevant. Where are we now? Block diagrams, definitely. You will have at least, well, either you will be given a system and asked to build a block diagram, or you will be given a block diagram and asked to apply the rules for simplification to obtain the transfer function, or both. So a block diagram will be there. And set 5, this, time domain analysis, definitely. Okay, first, second order systems, as I said, even if you get a third order, it will be given in such a way that you can analyze first and second separately. So you can simplify the problem to what we did in and we are still doing in these lectures 7 and 8. Now, set 6 may or may not be included, and that depends on, well, where we stop on Friday. Set 7, also called past exam questions, is definitely relevant. Yeah, so you have some nice modeling problems here. So this, for example, incorporates an electrical circuit here with a solenoid. So we have a resistance, you have L, inductance. Then you have a spring mass damper system here, and some questions related to that. Oh, this looks familiar. So you have a nice problem with a braking block, so you apply a force, and then this braking block, braking pad, hits, so you need to analyze. But here you are given a block diagram to complete. So again, the system itself is familiar, but the question is a little bit different. So this combines modeling and the block diagram. And so on and so forth. Look, my intention is for next Tuesday, first of all, I will provide you with one of the past mid-semester question papers. And on next Tuesday, I will try to solve it for you step by step with all your questions and comments that are most welcome. If there is any time left, then I will try some of these problems from the last tutorial set. Okay. But don't wait for me to do them. You are most welcome to attempt those questions and ask us. Yeah, see, a water tank system. Well, again, a coal loading system. So most of these problems, actually, they are not only useful for you to practice for the test or for the final exam. They're actually useful because they are real-life systems. So if you are ever wondering, while listening to me, does this have any application in real life? Does this make any sense? Well, here are the applications. So these systems can be very useful even after you complete this course. Okay, so that's enough. So unfortunately, I can't give you the full answer what will be in the test. I know what will not be in the test, which is linearization. And the rest you will know on Friday. Okay, so just quickly, what we did last week is analyze different systems under different inputs. So when you apply 4 different inputs, how those systems behave. We did the full analysis for first-order systems. So if the system is given as K or S plus A, which is a first-order system, then we applied each of these inputs listed above, and we realized how those systems behave. Okay? And we tried to separate the steady-state part from the transient part of the response. So all these little graphs on the right are responses. The first one is an impulse response, then step response, then ramp response. And we said, in case of an impulse response, the whole response is transient. Why is it transient? Because this exponential function has a negative argument. And the argument is also a function of t. So the larger the argument, the less the value of the function. So eventually, this will become 0. Step response has a clear separation between the transient part and the steady-state part, and so on and so forth. Then we moved to the second-order systems, and we made some definitions here that you already know, most of you, obviously. So you know what overdamped means, what underdamped means, what critically damped means. What I didn't check when I asked these questions, so let's just repeat quickly. If the system is overdamped, if the damping ratio is greater than 1, then the denominator has 2 real and different roots. Critically damped system has 2 real identical roots. Underdamped system has 2 complex conjugate roots. And undamped systems have 2 imaginary roots. Okay? And then we analyzed all of them for an impulse. And then we did a similar analysis as before. Then we said, OK, how about underdamped system with a step input? And we derived the expression for the output. And we said we will deal with this expression later in lecture 8, which will be today's second hour. OK, so let's see some other combinations of damping and inputs. Not all of them, but let's see some of them. Okay. So if we have a critically damped system, and if we apply a ramp input, critically damped means that there will be two real and identical roots in the denominator of the transfer function. The input is a ramp function, so we have 1 over s squared, 1 over s squared down here. So the output will be the inverse Laplace transform of this. We don't have this case in the tables, so we have to apply partial fractions. And when we do, we are going to get an expression like this. Now, you see that we already separated the transient part of the response from the steady state part of the response. So the transient part is the one that contains this exponential function. That means that after significant time has passed, this term becomes irrelevant. Or this term, this part of the response, two terms obviously. These two terms, so this part of the response, remains forever because this is not transient. So we call it a steady state part of the response. And you see that this is actually a straight line. So our response will eventually become a straight line, eventually. In mathematics, we call it asymptote. So this straight line is an asymptote to the whole function. OK, so let's see how this graph looks like. So if we separate these two parts, the part that contains this exponential is this one. OK, because when time equals to 0, the exponential part will be 1. This one will be 0, so you end up with 2 over gamma. So you start from 2 over gamma and eventually approach the time axis or approach the 0 value. The steady state part is this straight line. So it starts from minus 2 over gamma. It starts from here, and it's a straight line. The gradient is k over gamma squared. So we are combining those two functions, this straight line and this exponential. And this solid line is actually showing us the actual function, the actual output, the actual response, ramp response of this system. This line here, this dashed line here, is our input, our ramp function t. Unfortunately, it's not obvious. It's not obvious enough that these two lines are actually not parallel. Because the input has, the gradient is 1, and the gradient of the asymptote is not 1. It's k over gamma squared. It may happen to be 1, if we happen to have such values, combination of values, but otherwise it is not 1. Which is not the same as what we had before with the first order system. Sorry, I just said something completely stupid. With the first order system, you also had the input was t, but the gradient of the output is k over a squared times a, so it's k over a. So it is a bit different, but it is still true. So the input ramp and the steady state output ramp, they don't necessarily have the same gradients, whether it is a first and second order system. Okay. Apart from that, there is little we can find interesting in this graph. It is true that we would like to see gamma somewhere here. So how do we identify or 1 over gamma, if you wish. How do we identify the time constant? But the only way is actually to use the asymptote, find the intersection, use the slope of the asymptote, and so on and so forth, as we did in a few examples earlier today. Okay, so as I said, there is nothing we can do very much about further analysis of this system. Okay, now let's talk about some periodic functions being the input. So as we said, we are going to use a cosine function, cosine omega t. If you have an overdamped system and you apply a cosine input, the output is going to be this. This does not exist in the tables. Use partial fractions and see what you get. We are not going to do this in this lecture, but you can try for practice. Instead, we are going to analyze an underdamped system. So also, the input is going to be a cosine, but the system is underdamped. Again, a case like this does not exist in the tables. So partial fractions, remember how to do it. First fraction is a second order. So first denominator is second order. Therefore, you need a first order polynomial in the numerator, as plus b. Over here, again, you have a second order denominator. So the numerator has to be the first order. So you need to find 4 parameters, 4 constants, a, b, c, and d. Once you do, okay, so we are skipping that as well. Once you find the values a, b, c, and d, then you are able to find inverse Laplace transform of each term separately. And when you do, you get a lengthy expression here. So the function, the output, okay, we have a misprint here. This should be actually y of t, okay. So I'll try to remember to correct it. Please correct this. This is small y of t, because as you can see, it is a function of t, not of s. T, t, t. Okay. So the output in the time domain is what we have here. We just simplify a little bit. So K1 is actually something a little bit more complicated than what we have here. Now, although the function looks ugly, looks complicated, it's very hard to visualize when you look the graph of this function. Still, we can do the same trick as before. Separate this function into the transient part and the steady state part. Transient is something that will disappear after a while because of this exponential function, or exponential term. So this sine function has its amplitude dependent on time. Not only dependent on time, but actually decaying. So the amplitude is less and less. So these oscillations here on the right-hand side will disappear after a certain period of time. That is the transient part. So don't worry very much about the constant. This is what matters. This is what makes the amplitude less and less. And you have another sine function, but this sine function has a constant amplitude. Actually, the whole thing is the amplitude, apart from it. So this sine function remains forever. So all along the time axis, you will have that sinusoidal term existing. Constant amplitude. But what is also important to notice is that the frequency of this sine is the same as the frequency of the input. Just a confirmation that the system is linear. If those two frequencies are not the same, we don't have a linear system. Okay, so the frequency does not change. Frequency here is different, but that frequency will disappear, so we are not bothered. Okay, the steady state frequency is the same as the frequency of the input. Okay, yeah, apart from K1, we also have phi 1 and phi 2, so you have different phase angles, but again, that's not something that bothers us very much. And here's the definition of what phi 1 and what phi 2 is. There is an alternative way, but I don't think it's terribly shorter, than instead of having that polynomial indicating an underdamped system, you can actually have, how we call it, complete square term, but you still need partial fractions, and you are still going to get something very similar to what we got before. Again, a part that contains this exponential term, part that we call transient, and the part with a constant amplitude. Okay, just that these constants will have slightly different definitions. So if we try to plot this curve, let's combine the transient and the steady state first. Or let's sketch them separately first. So the steady state part has a constant amplitude. The transient part has the amplitude changing with this exponential function. So the transient part will decay after a while. Now these frequencies are different, so the periods are different. So it's very hard to show how they look when they are combined. So what we did here, we just said this is not accurate, if you can read this. This part is not accurate. So in the transient part, you have a funny combination of two sine functions with different frequencies, and one of them has a decaying amplitude, the other one has constant amplitude. So it's not easy to plot. And it is also not easy to analyze. But after the transient period, you end up with a periodic function with constant amplitude, the steady state part. Okay. Which is this one? Okay. Any questions? Okay. Now you can see that there are so many combinations we haven't covered. So I'll just leave that to you. Either use your intuition, try to deduce based on what you already know about different systems and different inputs, or just go step by step and derive the outputs. What? Okay. Now, lecture 8 is effectively an integral part of lecture 7. We are now going back to one specific combination. So we have a second-order underdamped system and a unit step input. And we are going to analyze this particular combination a little bit closer. So what we said earlier for that combination, where we effectively just derived the, second order. Yeah, we derived the output. So this is the system, this is the input. So this is the output here. And this is the sketch. This is how the output looks like. Now, several times I got the question, how about the time constants? This system is underdamped. We can't factorize the denominator to find the time constants. If you remember how you find time constants, you factorize the denominator, then rewrite the transfer function such that the denominator is non-dimensional, and then you read those coefficients multiplying s. They are time constants. In this case, you can't factorize, so how do you find the time constants? Well, why would you like to know? Why would you need to know the time constant? Well, remember that the time constant tells us how quick the system is, how quick the response is. And when you have a first-order system, it's very easy. You look at the time constant, and you know when the time reaches the value of the time constant, that's where the output changes by 63% of the maximum value. So there is a clear definition how fast the system is. How fast it is depends on the value of the time constant. But how fast is an underdamped system? You can't use time constants. Because if you apply the same definition, you will get a complex conjugate number as the time constant. So there are different indicators of the behavior of this system. Oh, I'm doing this. There are different indicators. So now we are going to define some of those indicators, those that we use in this course, but there are more than just 3 that we are going to define. So if this is the response of a second-order system to a unit input, unit step input, there are 3 things that are really relevant. One is, when is this first peak reached? So our response is going to reach a peak and then oscillate about a constant value, steady state value. So when is the peak reached, and what is the value of that peak? The time when the peak is reached, we just call it the time to the first peak. It's TP. How big the peak is, well, it may or may not be important, but we are actually more interested in the relative size of the peak, the size of the peak relative to the steady state value. So this length here is what we call overshoot. So how much the response overshoots the steady state value. And we normally use a percentage overshoot. Okay, so the difference between the peak value and the steady state value divided by the steady state value at times 100 to get percentage. Percentage overshoot. Very important property, very important thing to know about an underdamped system. Okay. Why is that important? Because if you, if you have a robot who is a second-order system, so that robot is supposed to do something, okay? So pick something from one place and put in another place, a robotic arm. Now, when it is going for this thing, if it overshoots by a certain number of angles and then picks it, well, it could be a very dangerous thing because there could be a technician standing there. Or it could be a wall. So, there is a damage that can be done due to the overshoot. Not to mention that actually after the overshoot, you have some oscillations, okay, until it grabs what it needs to grab and put it over there. So the overshoot, ideally you wouldn't have any overshoot with things that may be dangerous. But if you do, you need to know how big the overshoot is. I know. Or an example I use very often, if you have a, if you have a cruise control of a car, so you want to set 60 kilometers per hour because that's the speed limit. What if there is an overshoot? So it goes to 90 first, then down to 40, then 65, then 59.2, and eventually settles at 60. Well, it's okay. Steady state is good. It settles at 60. But in between, first of all, you're breaking the law because you're doing 90 without wanting to do that. And second, it's dangerous. It's not good for you. It's not good for other participants in traffic. So you need to know what the overshoot of your system is. And the last thing, last but not the least, settling time. So how long does it take before those oscillations disappear? If you think mathematically, the answer is never. There will be always oscillations. It's only the amplitude getting smaller and smaller, eventually getting microscopic, but it's there. The amplitude is there. So we have to apply a certain criterion. When can we say the oscillations don't exist anymore? As far as we are concerned, those oscillations are not relevant. And the usual criterion is 2%. So when the amplitude becomes 2% of the steady state value. That's what we call settling time. After that, we can ignore the oscillations. Now, this 2% is obviously an arbitrary number. If you are interested in very, very accurate behavior of the system, you will probably have 1% or even less. But 2% is a standard for settling time. So if you don't say anything, if you just say calculate the settling time, we mean 2%. If we mean something else, we will stress that out. So these are the three parameters of this combination, as I said, second-order system and a unit step input. Okay. Let's see now. So a few steps back to what we did last week. Find the output first in the S domain. Now find the inverse Laplace transform to get the output in the time domain. Here it is, as we already derived. So you have a sinusoidal function multiplied by this negative exponential with a negative argument. So we have a transient part, which is this. And we have the steady state part, which is a constant. So this gives us the steady state value. So our output oscillates about this particular value, k over omega n squared. We also have a definition for phi, which we took from the Laplace transform tables. How do we find the time to the first peak? Well, like any function, you want to find the maximum. The best way to do it is find the differential, make the differential equal to 0, and solve for time. So we will need to differentiate this function and make it equal to 0. So y dot of t equal to 0. To do that, maybe the best thing to do is expand this sine function. So treat it as sine A plus B. Sine A plus B equals sine A cosine B plus cosine A sine B. I think we had that in previous lecture. Anyway. Okay. So here it is, rewritten. Then, when we find the derivative of y of t, and when we make it equal to 0 and make time equal to Tp, we are going to end up with this much simpler expression, that simpler equation that we need to solve. So sine of omega t times square root of 1 minus xi squared times Tp. What is Tp equal to? Well, first of all, for sine to be equal to 0, the argument of the sine needs to be equal to n pi, but we are really interested in the first peak only. So we're not interested in the third or fifth or 10th peak. We want to find the first peak because that's the biggest peak. That's where the overshoot is. So n equals to 1. Therefore, time to the first peak equals to pi over omega n square root 1 minus xi squared. This equation will be given in your test paper and possibly final exam paper as well, if necessary. So you don't have to worry, how did he really differentiate this? You know, is this, you know, you can check this by all means, but actually that's not what we expect you to do in the exam. If you have a second order undamped system and you have a unit step input, just use this equation. Time to the first peak. As you can see, the time to the first peak depends on the properties of the system, the natural frequency and the damping ratio of the system. Okay, now percentage overshoot should be simple. So we want to find now the peak value. So if you know the value of time, we just substitute Tp into the expression for y of t, and we'll get the peak. We'll get the maximum. Okay, so back to this expression, just wherever you have time, t and t, you should put Tp, the expression for Tp. Okay, so here is the expression for MP. Okay, we can simplify that because sine of pi minus phi is still sine phi, right? On the other hand, remember that phi Well, remember, did you realize that phi equals sine -1 of square root of 1 minus psi pi? Well, how do we know that? Well, from here. This is phi, as defined in the Laplace transform tables. This is sine, this is cosine. Tangent is sine over cosine. Okay, so this is sine phi. Okay, so that helps us eliminate this and this, sine of inverse sine of omega n square root 1 minus psi squared. So we end up with this exponential term and this steady state part here. That's the peak value. But we want the relative overshoot. So the value of the peak relative to the steady state value. Steady state value is this, k over omega squared. This is the steady state value. This is what is left after the transient oscillations disappear. If you remember, there are other ways to find the steady state value by using the final value theorem. But just by looking at this equation, we see what the steady state value is. OK, so we have the expression for MP. We have an expression for M. Percentage overshoot is the difference between the two divided by the steady state value and obviously times 100. So when we do that, we'll end up that percentage overshoot equals 100 times this exponential term. Again, another expression that will be given in your exam paper. So not something you have to derive. What is important, why I highlighted this psi, is that the percentage overshoot depends only on the damping ratio of the system. What is not obvious, because you have a minus here, then you have a square root with a minus sign down here, so it is not clear whether bigger damping ratio gives you bigger overshoot or smaller overshoot. What do you think? I mean, damping ratio is still between 0 and 1, excluding 0, excluding 1. But is the overshoot going to be greater if the damping ratio is 0.1 or if it is 0.9? Okay. The more damping, the larger the damping ratio, that means you have more damping. Therefore, you have less overshoot. You damp the system better. So if the system is just, if the damping ratio is just positive, 0.1, you're going to have a huge overshoot. If it is 0.9, it will just going to appear above the steady state value and quickly return back. Okay. But it will depend. It does not depend on the natural frequency of the system. Only depends on the damping ratio of the system. OK, and finally, settling time. So how long does it take until the amplitude becomes 2% or less? Until it becomes 2% of the steady state value. Well, again, I emphasize this, amplitude. When does the amplitude becomes 2%? Amplitude, well, OK, let's get, amplitude is this. So for this analysis, we ignore the sinusoidal part. We ignore the steady state part. This is the amplitude. We want the amplitude to be 2% of the steady state value. OK. So amplitude has to be equal to whatever we decide the criterion to be. For this particular case, we agreed it was 2%. OK. At time, when this call expression equals to x, that's when the time equals to ts, settling time. So if we want to resolve this for Ts, we need to find the logarithm of the left-hand side and logarithm of the right-hand side. We are talking about natural logarithms, obviously, because of the exponential. So we get that Ts will be equal 1 over xi omega n times logarithm of 1 over x times square root of 1 minus xi squared. We can expand this logarithm. So Ts becomes 1 over xi omega n, brackets, logarithm 1 over x plus 1/2 logarithm 1 over 1 minus xi squared. Okay. What next? Well, we can leave this as it is, or we can say, we can start thinking this way. If the settling time is a significant value, that means we have a low damping. As we said, systems that are not well damped, so have 0.1, 0.2, 0.3 even. First of all, they have huge overshoot. Then settling time is much longer. It takes longer to settle because the damping is not good. So if Ts is of any interest, that means we don't have a good damping. So we can assume that the damping ratio is less or equal to 0.3. If you assume that, then this term becomes very close to 0, so we can ignore it. Sorry, no, the other way around. This term, this term will be very small, will be close to 0. Why is that? Because if psi is small, less than 0.3, then 0.3 squared, or even less, is 0.09. So you can regard it as 1. 1 minus something very small is still very close to 1. 1 over 1 is very close to 1. Logarithm of something very close to 1 is very close to 0. So this part can be ignored. I apologize. This part is ignored, so you end up with natural logarithm of 1 over x. And we said that x was 0.02. So if you substitute that value, we'll end up with Ts being equal to 3.91 over xi omega n. This equation will also be provided in the exam paper. But you have to be careful. This is reasonably accurate for low damping values, 0.3 or less. Okay. Now let's do some examples. So you're given a system here, a transfer function, and you're asked to find time to the first peak, percentage overshoot, and settling time. First thing to do is check whether this is the right system for you. Is this system really underdamped? So what we are going to do first, let's normalize this transfer function. So let's divide by 0.01, both the numerator and denominator. So this is the normalized form of the transfer function. For the system to be underdamped, the roots of the denominator have to be complex conjugate. So if you find the roots, we get a pair of complex conjugate numbers. So the system is indeed underdamped. So we can apply this analysis. Okay. There is another way to check the same thing, and that is check the value, try to find what the damping ratio is. It's not obvious straight away. So what you do is equate this with omega n squared. So if omega n squared is 100, then omega n is 10. Then equate 5 with 2 psi omega n. 2 psi omega n equals to 5. Now you know omega n, so you can find that the damping ratio is 0.25, which is less than 1, more than 0. Perfect. Now we know for sure that our system is underdamped. not only is it underdamped, also damping ratio is less than 0.3. So we can safely apply the equation for the settling time. And now we just substitute the values of the natural frequency and the damping ratio into those three equations. Tp, we already derived that. Time to the first peak, when we substitute the values, we get 0.324 seconds. So this is how long it takes for the system, for the response to reach the peak, the first peak. How big is the peak? Well, again, take the expression for the percentage overshoot, substitute the values for the damping ratio, and you get a reasonably large overshoot, 44%. So the damping ratio of 0.25 gives you 44% overshoot. So you're starting to get some ideas. And settling time, applying this equation, gives you 1.5 seconds, 1.56. So slightly over 1.5 seconds until we can say that those oscillations are non-existent or irrelevant. Okay, so that sounds simple. Any questions? Oh, yes.
Magnitude of the imaginary part have any physical significance?
Oh, well, it does. The magnitude of the imaging part.
The S, yeah.
Yes. Yes.
Why? What does that determine?
Well, it does have, but we have to. Okay. I mean, it has to have a part because it depends on what you have here. So it has significance. It also depends on what you have here. Apart from, so what is the imaging part? It's b squared minus 4 ac, where a is 1. So b squared, so it does depend on the damping ratio. It does depend on the natural frequency. Apart from, the relationship is not so obvious to say, OK, this number means whatever. But the information contained here is definitely relevant because it contains both the damping ratio and the natural frequency. Actually, your question will become relevant very soon. But itself, the imaging part itself is not enough to tell us everything we need. We need to combine it with the real part, which again depends on this, which depends on damping ratio and the natural frequency as well. Yeah. Now you got me thinking. So damping ratio is inverse cosine of imaginary of S over real of S. Oops. From memory. But that, as I said, will be relevant probably after the test, lecture 11. Yeah, so at this stage, this doesn't help you very much. Okay, any other question that I can't answer, clearly? If not, have a look during the break at this example. So we'll discuss it after break. Okay. To look into a system that you can't see. Okay. So look into this system, the example that was not solved in the lecture. No, no, 5.2. 5.2. Okay. Did you print from here?
Yes.
And you didn't change anything in Washington. I know it is.
This is 7.
Oh, okay, yeah. Oh, okay. No, it's down. Down here. It's under dance with the cosine. Oh, phi 2, phi 2. Phi 2. Yeah, phi 2. Although the whole thing, while we are skipping steps here, just to give you the basic idea. You know, I mean, getting to this and this takes a lot of time. Okay, but you're right.
Yeah, it was just confusing.
Correct. No, okay. No, we ignore this part. K over gamma square, we ignore that because it is just a scaling factor as you call it. So you will still have the same shape, just everything scaled by whatever number you call. So the analysis is for this. Sorry, he was okay. Because here, very good, okay, it's good time, okay. How do we know this? No, we don't need, we know this from the table. Okay. So when you use the tables, you don't ask questions why. No, you're just using the tables and continuing your work. Okay, we can think about why this is so. That's our spare time. But you know, so let's just accept this is true. If this is true, then this is sine. Sorry, and this is cosine. So that's how we know. From the definition of phi, the definition of the phase. So if sine phi equals to this, so equals to this, then I'm just going to use it. Where did I use it? Here. Phi equals inverse phi.
Sine inverse something equals to 1.
No, sine or inverse sine equals to this, so whatever is left. It is equal to this, sorry.
That part cancel with that
Cancel with that one because it is exactly the same. So we end up with only exponential.
And do you just pick up only pick up the steady state?
No, now I say this minus this. Okay?
You like running with that answer.
Okay, because that's the steady state value. If you look here, okay, this is the steady state value. Okay, this is the transient part. So this sine or cosine, they oscillate about this value too. Okay. Or you can use the final value theorem. Go back to the S domain and use the final value theorem. You will get k over omega squared. Yeah, I mean that's set 2 for you. So if you get, so how do you find, you need to find a limit when s approaches 0 of this times x. Okay, so s and 1 on s will cancel. So if this is 0, this is 0, you end up with k over omega squared. Which is a steady state. So don't forget what you learned. Just keep learning more. Like every other thing you learn. Okay. Sorry. So. Okay, you're happy. No, where are we? That sine. Okay, you're happy now with this. No, sorry. That from this. Why are you confused? But tangent equals sine over cosine. Okay. So tangent phi equals sine phi over cosine. It also says here that it is equal to square root of 1 minus psi squared over psi. Yes. So what I'm doing now, I'm saying that this equals to this. Okay. And this equals to this. take the whole function.
Why don't we focus on this?
No. We take the whole function and differentiate it with respect to time. When we do that, this will give us 0. That's why we have, so that's why we ended up with it. Okay? And that part, now we make it equal to 3. And that's how we found TP.
I mean, TS.
TS. Oh, TS, okay. Because TS is the time when the amplitude becomes 2% of the steady state. Amplitude, not the whole function, but just the amplitude. If that's how we define TS, then we are only interested in the amplitude. So when is this going to be equal to 2% of the steady state? Okay, so we are staying with the amplitude. We are not interested.
So it must be 2%
Of the steady state value, yeah.
I remember we did this.
Yeah, X. We decide that X is 0.0. The X is 2%. In a more general case, it can be different. It doesn't have to be 2%. But if it is 2%, then this analysis is correct.
All right. Okay.
Because we said origin. So we just check whether it is green. Okay. All right. I realize you have all solved this problem. This one. So let's just check whether you are correct or not. So we want to find the time to first peak, the percentage overshoot, and the settling time when we apply a unit step input to this particular system. Okay, so what do you suggest as the first step? Normalize, thank you. So multiplying by 16 will do the magic. Is this a bit too loud? So we have S squared, sorry? Oh, okay. So multiplying by 16 will give us 1 over S squared plus 10S plus 16. What do we do first? Do we apply the equation for the time to first peak or percentage overshoot or settling time? Or Well, obviously, so this is the transfer function. So if you apply, if you stay with the same terminology, y of t will be inverse Laplace of 1 over s squared plus 10s plus 16. Okay? So we can find this function. But the trick is not to do this. We want to use whatever we have in the S domain to find the parameters we need. Time to the first peak, percentage overshoot, and settling time. So that's the whole idea. I mean, in the lecture we derive them, so we don't have to derive them in the exam. But you need to know how we got to those expressions. So we want to use whatever we have here to find those three values, those three parameters. So Tp will be a function of omega n and psi. M percentage will be a function of psi only. And Ts will be a function of omega n and psi. What exactly those functions are, we can have a look a bit later. But before we apply these, we have to check one very important thing, that the system is underdamped. Because if it is not, we can't apply these equations. Is that a question, sorry? No. No, you're doing this. Okay, that's okay. Okay, so is this system underdamped? So there are, if you remember, there are two ways to do it. Either check the roots of the denominator and see whether they are complex conjugate or not. Or actually find the damping ratio by equating this with, in this case, obviously 1 over s squared plus 2 psi omega n s plus omega n squared. So we want to compare this with this and this with this. Okay. Or if you want to be very correct, let's write k here. So you also want to compare this with this. But for this analysis, k is not relevant. You don't have k here or here or here. So k is not that important. So where are we? So if we equate the coefficients, then we say that omega n squared equals to 16, which makes omega n equal to 4 radians per second. Then we can say that 2 psi omega n equals to 10, comparing these two coefficients, which makes psi equal to 10 over 2 times 4, which is 8. 10 over 8 is what? 1.125. No, 25. 10 over 8 is 1. You have 21.25. But this is greater than 1. If it is greater than 1, the system is not underdamped. You can't use these equations. So the step response would be something like this. No overshoot, no time to the first peak, no settling time, nothing. So you can't apply the same analysis anytime you want. Just because the system is of a second order doesn't mean you can automatically apply these expressions. Okay, so that's why That's why we said here, and be careful. So the system has to be underdamped, and the input has to be a step. Otherwise, forget these three equations. Okay. Any questions? Comments? Oh, yes? No, because TS, the criterion for TS is that the amplitude is 2% of the steady state. Here you don't have an amplitude. You can introduce your own criterion and decide that whenever the output becomes, enters this particular range, it's not really settling time, it's something else. I don't know how you want to call it. But you can introduce some criterion and say, okay, when this happens, this is T1 of some sort. Apart from, this is not a standard criterion. TS is a standard, literature thing. Okay, and one more feature of underdamped systems, or step responses of underdamped systems, is so-called logarithmic decrement. Now, sometimes you have a situation when you are recording the response of an underdamped system, but you don't capture the whole response from time equal to 0 to time equals to something very high. So you are able to record only a small part. The minimum requirement is that you record at least 2 peaks, if not more. You can still use this information to find something relevant about the system, to find the damping ratio in this particular case. The damping ratio. And the natural frequency. Okay, so let's see how it is done. So if this is what you recorded, then you can read the value of the first amplitude, the value of the second amplitude. Obviously, the second has to be smaller because the system is underdamped, but still damped. So the amplitude is decreasing with time. And you also measure the time between those two consecutive peaks, capital T. So A, B, and capital T are known values to you. Although you don't know the overshoot, you don't know when the first peak appeared, or what was the peak, what was the overshoot, but you can still determine the system. Okay, so back, we can scroll back a few pages, but you'll find that this part is the transient part of the response. Over here. So this is the transient part. This is what oscillates. This is what we have recorded on that little graph. We may not know exactly the value we have here, but this is the recorded part. Okay, so this is the transient part. Now, thinking about amplitudes, each amplitude will be this constant will not change, but will be proportional to this exponential term. So first, amplitude A will be proportional to exponential with T1 in the argument. Amplitude B will be proportional to this exponential term, but this time T2 will be in the argument. And the ratio of the two amplitudes will be equal to the ratio of these two exponential functions, which will be equal to e to the minus xi omega n, and then you have T1 minus T2. So all you need is the difference between those two times, T1 minus T2. This ratio of two amplitudes is called logarithmic decrement. Okay. So that's something you measure. You measure from the graph. You measure A, you measure B, and find the ratio. So R is obviously going to be greater than 1 because A, the first amplitude, is greater than second amplitude. Capital T, which is the time between two peaks, that's also what you measured. Okay, now let's take the logarithm Okay, let's take this equation here and take the natural logarithm of the left and the right-hand sides. So on the left, you will have minus psi omega t times t1 minus t2. On the right, we will just have logarithm r. From there, we will express psi as 1 over omega n capital T, because this is capital T, right, times logarithm r. Now, we can also express t, because t is the period of those oscillations. That's the period. That's the time between two peaks. And the period can be obtained from the frequency. Sorry. Okay, the frequency is omega n times the square root. That's the frequency of the output. Omega n is the natural frequency of the system. It is the property of the system. But the frequency at which the output oscillates is omega n times square root. Okay, so that, if the time is the period, it will be equal to 2 pi over this frequency that we, by the way, call damped frequency. Okay. Now, if psi is much less than 1, which is a very reasonable assumption to make, because if these two amplitudes are similar in size, obviously are not equal, but you don't have the first amplitude much bigger than the second one, that means you don't have a very high damping. Obviously, this system takes a while to settle. So the damping is not very high. So let's assume, very safely, that damping ratio is much less than 1. If that's true, then this square root becomes 1. Because here we have something which is much less than 1 squared, as we had earlier. So then we can say that that t equals to 2 pi over omega n. So that's what we are going to put in here. So now psi becomes 1 over omega n times omega n over 2 pi, okay, reciprocal of t, times ln r. So finally, the damping ratio is 1 over 2 pi times ln r, where r is the ratio of the two amplitudes. Okay. So just by observing the output, observing the oscillations, we can find the damping ratio of the system. Here is an example, a very simple one. You have two amplitudes. One is 2.4 centimeters. The other one is 1.9 centimeters. What is the damping ratio of the system? Now, of course, you should always be careful with units. But because you are taking a ratio, as long as the units are the same, you don't have to convert into meters and then apply. Okay, so the ratio is 1.263. Damping ratio, just apply this equation, which will be given in the exam if you need it. So you get 0.037, a very small damping. Okay. And that's really all about time domain response. How we link what we know in the S domain, what we know about the system, and what we see in the transfer function with the characteristics of the response of that system. Any questions? Okay, then the last lecture for this week, we won't finish this today, obviously, is analysis in the S domain. I know why I left frequency. I actually prefer a complex domain. But maybe actually you should get used to different terminology for the same thing. Okay, without too much introduction, so we want to see more about the properties of different systems if we are only working in the S domain, without going into time domain. So looking into the S domain characteristics, we want to find something about what is happening in the time domain. Let's start in an electrical circuit. This time we are going to introduce an amplifier. Apart from that, you have a resistor and capacitor as we had before. So if the input is voltage VI, here we'll have K times VI. That's all that this amplifier does, nothing else. The output is VO. Analyzing this loop here, K times VI will be equal to, okay. We are skipping a few steps here, but so the voltage will be equal to Ri over here plus VO. On the other hand, this loop will tell us that VO equals to 1 over C integral I dt. Okay, so we already know that. Or, in other words, I equals to C VO dot. So when we eliminate I between those two equations, we are going to get this differential equation. So this differential equation is the mathematical model of this system. It describes this system. Now we want the transfer function. We apply Laplace transform to the left-hand side. We apply the Laplace transform to the right-hand side. However, because we want to find the transfer function, we assume initial conditions to be 0. So here is our transfer function. So this is a first-order system. First-order system, because the denominator is a first-order polynomial. Okay. This denominator is also called characteristic equation. Equating the denominator with 0 will give us a characteristic. So sorry, the polynomial is called characteristic polynomial. When that polynomial equals to 0, we are getting a characteristic equation. So so solving the characteristic equation, making this equal to 0, will give us S equals to minus 1 over CR. S is a complex variable, remember that. But in this particular case, it is a real number. Complex numbers are expressed in a complex plane. So you have a real axis, and you have the imaginary axis. This particular number has the imaginary part equal to 0, and the real part is obviously a negative number, because both C and R are positive numbers. So this number is somewhere here. So it is on the real axis and on the left-hand side of the plane. So left-hand half of the real axis. So it is negative. Okay. Now let's see what that means in the time domain. We kind of know it, but we'll try to relate the location of this root in the S domain with the behavior of the system in the time domain. Let's use the simplest possible input, which is a unit impulse, just to see what is happening in the time domain. So when we apply unit impulse to this system here, you know how we deal with that. How do we go into time domain? You need to multiply the transfer function with the input, which is 1, find the inverse Laplace transform, and here is the output. Just check the tables if you're not sure. So in your tables, you will find that the output is actually a decaying exponential function. Okay. So there is a clear relationship. Now we are going to expand this to second-order system in a minute. But there is a relationship of where the root is in the S-plane to how the system behaves. We don't have the full picture, but at least we know this, that if the root of the denominator is a negative real number, we are going to have a decaying exponential behavior. Now, example 2, second order system. Now, let's take, again, a spring mass damper system. Force analysis, so analyzing the forces acting on this mass, you will have force pulling down, the input force. The spring and the damper will be resisting that force, and then you have the inertia term as well. Apply Laplace transform, assume zero initial conditions, so the system is at rest, not moving. And this is the transfer function. Now, find the roots of the denominator. The roots of the denominator will depend on the values of C, M, and K. So these are the two roots. But depending on the relationships between C and M, M and K, K and C, so the combination of the values, you may have different kind of roots. Okay. So first case, if C squared over 4 is greater than MK, back here. That means that the discriminant, the argument of the square root function, is positive. That means that the square root gives us a real value. And now you have another real value here. So you have minus one real value plus minus another real value. So you're going to have two real and different roots. Okay. So that means when we say region A down here, that means that your roots, one root will be somewhere here, the other root will be somewhere here. So that's the case when C squared over 4 is greater than MK. That's region A. So our roots are now still on the real axis and still on the negative half of the real axis. But this time we have two, and those two are different. They're not identical. Case B. When the discriminant equals 0, when C squared by 4 equals MK. So in that case, this is 0, so the whole square root equals to 0. So the roots are minus C over 2m plus minus 0. So you have two identical roots. They are still real, they are still negative, but they are identical. So that's region B. That region B is only one point. That's where both roots are. So they are on the S-plane, they are on the negative side of the X-plane, of the S-plane, but they are at the same place, at the very same point. So we call it region B, but it is really only a point. Case C, when C squared over 4 is less than MK, this expression here becomes negative. If this is negative, then you have a pair of complex conjugate roots. So you have a real part, and then you have an imaginary part. Actually, you have two. One is positive, one is negative. So the real part is negative. Imaginary parts are one positive, one negative. Obviously, they have to be symmetric. And that is this region C, here and here. So your roots are still on the right-hand side, on the left-hand side. I have to turn around. So the roots are still on the left-hand side of the plane, of the complex plane, but they are not on the real axis anymore. They are removed, one up, the other one down. So this is the case when MK is greater than C squared over 4, or the discriminant is negative. Okay. What it means in the time domain. Remember back, if you apply a unit impulse to this transfer function, you have different cases where the system is overdamped, critically damped, underdamped. Okay, so in the first case, when the roots are real and different, this is what you are going to have as the output. Capital A, capital B, don't worry about those ones. We know they are constants. So let's not think very much about them. But you have a combination of two exponential functions. Each exponential function corresponding to one of the roots of the denominator. Second case, region B, when you have two identical real roots, the output will look like this. Again, K1 and K2 are some constants, don't bother. But you will have, one term corresponding to this exponential, and the other one, you have a product of t times exponential. Third case, region C, when you have a pair of complex conjugate roots, then you will have a sinusoidal output, but with damped amplitudes, with damped oscillations. So there is a relationship, clear relationship, between where the roots are in the S-plane and how the system behaves. Now we'll try to spread that picture to the whole of the S-plane, of the complex plane. So here are the axes. This is the real axis. This is the imaginary axis. What we found so far is that if the roots are on the real axis and on the left, you will have exponential behavior, non-oscillatory behavior. What we didn't check, so I hope you will accept this or believe me, that the further away from the origin, the faster the system is, the response is. So you see, this takes much longer to reach zero. This one is much quicker. If we move away from the real axis, then we are getting these complex conjugate roots that result in oscillations. Okay, oscillations all over the place. So on the left-hand side of the S-plane, you have damped oscillations. Okay, damped oscillations everywhere. The difference is that the more you move away from the origin, the more you move away along the negative side of the real axis, the better the damping. So you see that this overshoot is greater than this. But as you move along the imaginary axis, you are increasing the frequency of the response. Think about this omega. It's actually frequency. So the more you move along the omega axis, the higher the frequency or the shorter the period.
Is there a difference in it being positive and negative in the
No, because they always come in pairs. So this one is the same as this one. They come together. If the drawing is not exactly the same, that's my fault or whoever did this. But this is the same as this. And same over here. This one is supposed to be the same as this one. This one's supposed to be the same as this one. Because they always come in pairs. If they are complex, they are conjugate. You can't have one without the other. You always have the mirror image. Whereas if you have a real, you can have only one real, or you can have three real numbers. Okay. But now, this is only one half of the S-plane, one half of the complex plane. What if we have at least one or more than one roots on the right-hand side? First, let's stay on the real axis. So if you have a positive root, then you still have an exponential response. But this exponential response deviates, goes away from the zero. It doesn't come back to zero. It just keeps deviating until infinity. You know why? Because now you have plus alpha t. exponential to a positive power will give you an ever-increasing exponential function. And the same here. And the further you move along the plus real axis, the faster you have this exponential growth. This is what we call exponentially unstable system. This one is exponentially stable because it comes back to 0. This one too. This one doesn't. If you move away from the real axis, you have a pair of complex conjugate numbers. Again, you have 3 pairs. But the real parts are positive. If the real parts are positive, you still have oscillations. But the oscillations have ever-increasing amplitudes. So the amplitude is bigger and bigger. Again, why is that? Because here you have e to the plus something, plus alpha t. So you still have oscillations, but the amplitude is getting bigger and bigger. So these systems are also unstable. So we call them oscillatory unstable. Okay. And finally, special cases. What if we have a root right on the imaginary axis? So real part is 0. This is a special case. We call it neutral stability. Neutrally stable. The system is neutrally stable. Here you have the response not coming back to 0, if it is an impulse response, not deviating into infinity, but staying at a new constant value. So it's neither stable nor unstable. It is neutrally stable. So you can call this a special case of exponential function. Okay, but the argument is 0. No, it's over here. This one is 0. Okay, so therefore constant. These two roots, so real part is 0, will produce oscillatory behavior with constant amplitude. So what we called undamped case last week, damping ratio equal to 0, is actually a case of neutral stability. This system is neither stable nor unstable. The only difference is if you move away from the origin, you get higher and higher frequency. But it will still, this frequency will still have constant amplitude. Okay. So try to grasp this. Of course, a reminder, what S really is, it is a complex number. It is a complex variable. Okay. So here's what we said about stability. Stable on the left-hand side, unstable on the right-hand side. Now, in practice, depending obviously on the application, we always like to be safe. So we like to move away from the boundary of stability. So we want our roots to be safely away from when the system may be unstable. For this course, we will be dealing with the theoretical case only. So as soon as your root is a little bit to the left, it will be regarded as stable. If it is a little bit to the right, it is unstable. If it is right on the imaginary axis, it is neutrally stable. Okay. Now, do you have any questions? While you're thinking about questions, I just hope this is long enough to demonstrate an unstable system. Here it is. I don't know whether you ever thought about this. This is an unstable system. Why? Because if I manage to put it in a sort of equilibrium, which I can't, and I apply an impulse input, it exponentially deviates from the original equilibrium. Okay. It never comes back. This is a case of a stable system because you apply an impulse and it will eventually settle. So this is a case of oscillatory an oscillatory stable system when you have a pendulum. But this is a clearly unstable system. We knew that. We never thought about defining it that way. Okay. We are all unstable. I'm unstable. If you apply an impulse, which is strong enough, I will obviously fall down. Yeah. If you are not careful with some, substances, you become very easily unstable. Now, why don't I fall down, every few minutes, every few seconds if I'm unstable? Because I'm adjusting the input. You think about it, if you're standing for too long, and if you feel you're losing balance, you just move your foot, and you think it's okay. You think you're stable. No, you are unstable, but you are able to adjust your inputs every now and then. It's like balancing the stick. I mean, everyone can balance a stick like this for a few minutes until they get tired. But what we are doing, we are adjusting the inputs here. So keeping the unstable system still under control. If this is exponentially unstable, that means the system has at least one real root on the right-hand side of the S-plane. Maybe two, maybe even more, but at least one. There are no oscillations, so there are no complex conjugate roots. Okay. Any questions? No questions. Oh, yes. Okay.
For the system with damping ratios smaller than 1, do we treat this as neutrally stable?
No. With damping ratio less than 1, no, it is still stable. Okay, maybe, yeah, thanks for asking that. Let's just recap what we said about the damping ratio and the location of the poles, of the roots in the S-domain. These roots, if we have a second-order system, so for the damping ratio to be relevant, we need a second-order system. Second-order system means 2 roots of the denominator. Now, if we have 2 roots on the real axis and the left-hand side of the real axis, we have 2 different real roots, so the damping ratio is greater than 1. So we have an overdamped system. If you have 2 real roots both at the same time, at the same place, then we have 2 identical real roots, and negative, obviously. Then we have a critically damped system, damping ratio equal to 1. If the damping ratio is less than 1, we have a pair of complex conjugate roots where the real part is negative. So we have this and this. So the system is still stable because the damping ratio is greater than 1. Greater than 0. The damping ratio is greater than 0, the system is stable. The fact that it is less than 1 means there will be oscillations, but oscillations will be damped. So the system is stable. So this is what we call a stable system. Oscillations are damped. So eventually they disappear. So only if the damping ratio is 0, like, for example, this pair of complex roots, then we have neutral stability. So damping ratio is 0. That's neutral stability. Damping ratio negative, that therefore my question in the beginning. Damping ratio is negative, then you have unstable, either exponentially or oscillatory unstable behavior. Okay. Any other questions? Okay. I know you like to finish earlier. So we'll leave this for Friday. I don't mind finishing earlier from time to time, but yeah, not too often. No, I saw her working on the rig, just this morning. But I still can't tell you. No, sorry. Okay, Q&A. No way. Sorry, that's Dr. Kwok. Yeah, okay. I think I said some technical stations. I probably should have put that into another list. Okay. But also course outline. You have this in course outline. Perfect. Sorry, before yeah, sorry, teacher. No, it's not maybe anymore. I'm just not doing lecture 10. So lecture 10 you can exclude. Lecture 10 is, well, not really. It's steady state errors. And they are quite independent from everything, apart from obviously classifiers. So yeah, lecture 10 will be excluded from the mid-semester test. Oh. I don't know. You get the spring mass done for the system, and then we ask you, well, is the value of
你还是问这个问题？
what is the value of C that
不是你跟我说420里面讲的 mutually stable 是什么意思？就会有我。
Like, provided that you've done.
Yeah. So for the one we just provided on Monday, he told us that's mutually stable when the system is trying to get back to the new.
Oh, right. Oh, well, now you're
That's
going.
why I'm asking
Well,
that.
there is one thing I tell these guys and one thing I tell the 40th students. Okay. So, and then
So
it's
the
up to you.
concept-
No, then it's up to you to decide when I'm lying. Third year or the 40th. No, I'm kidding. I'm kidding. Okay. No, this is what I'm saying. Okay. If you have a small perturbation, but maybe you can just write as a vertical line, then the question is with the aircraft. Okay, does the aircraft return back to equilibrium? Then it is stable. Does it deviate away from the equilibrium? Then it is unstable. Or if it resumes a new equilibrium, which is this case, then it is neutrally stable. Because remember, before this you had zero. Okay, then you had an impulse. That's why it jumps and then goes down. So this zero is equilibrium. So when it comes to aircraft stability, we say, okay, you're flying, you have a gust. Does the aircraft return back to equilibrium? Does it keep deviating away from the equilibrium, or does it just resume a new equilibrium? Which is in accord with what I'm saying here. It's just you want to move.
So like for the aircraft, it's not a transit. It's gradual.
No.
Is it?
No. Transit, it's different. No. What I was telling them is not only with transit. It what happens eventually. If eventually after the transit, the aircraft is back at the equilibrium, the system is stable. But that's what you have here, or here as well. This is transient that eventually becomes an equilibrium. So sorry if you're not aerospace people, but I'm just, just trying to relate what I'm doing in aerospace with stability of aircraft. It's actually the same thing. Aircraft is a system, like air conditioning, like car, like a ship, like. No. Sorry, you think about the aircraft?
Yeah.
So just really quick, so yeah.
我可说来了。你这个图上为什么是？你这图上为什么是？
Oh, okay. This